Yeah, thank you very much. Okay, so I guess um, yeah, so this is a subject that I didn't know much about before lockdown, and I still don't know much about it. So I'm probably missing out lots of stuff. But I thought it's a good thing to talk about because I think there is um, a lot of potential for people to come up with new theorems in this area, and I'll suggest some directions as we go along. So here's sort of what I knew before COVID. So what's an integral point? We're going to have k is going to be a number field, OK is going to be its ring of integers, and S is going to be a finite set of places, and OS is going to be the ring of S integers. So it's the elements alpha in your number field where the valuation of alpha is non-negative at all the prime ideals not in S. So if you take your S to be the empty set, OS will be just the ring of integers of K. And V is going to be a variety over K, and it's not going to be really important. These words aren't really important, but let's just say it's smooth and projective and irreducible. And W is going to be a subvariety defined over K, but W doesn't have to be irreducible. Okay, now so I'm going to take what you might think of as a punctured variety. So I'm going to puncture V along W, and the set of S integral points, well, the set of K rational points on this are what you think they are. They are points on V that aren't on W. But the set of S integral points on V minus W, they're the points, the K rational points on V, such that the reduction of modulo any prime that isn't in S is not in W. So I want things that don't reduce to W modulo any prime, apart from possibly the primes belonging to S. So if you haven't seen this notion before, it looks strange. So let's see an example to make it look more natural. So if you take a Weierstrass elliptic curve, so y squared equals x cubed plus ax plus b plus the point at infinity, and a and b are going to be integers that where the discriminant is non-zero, and I look at I look at the punctured curve, which is the same as the affine curve, so it's e minus infinity, and the integral points on those, well, they're going to be rational points that don't reduce to the point at infinity. So they're rational points where there aren't any denominators at any the valuation is non-negative at all primes. So there are points where
there is a question in the chat.
Oh, what
Alex, maybe you want to ask the question.
So, Samir, you're thinking of V as a scheme over OK, or at least OS? And
yeah, maybe I should have. Yeah, exactly. I'm just ignoring some subtleties here, but of course, maybe just think of V as being defined by a set of equations where the coefficients are in the ring of integers of K. Thanks, Alex. Okay, so here, you end up with, exactly as in here. Okay, so you end up with points with integer coordinates, which is what you might think of as an integral point. If I just gave you this affine equation. And of course, if you don't subtract any points, then the integral points are the same as the rational points. Okay, so here's sort of basically what is known for curves. So if you start off with a smooth projective curve and you choose a bunch of points, I've made my points in CK, but actually they don't have to be. They could be in CK bar, but stable under the action of Galois. Okay, so you puncture C at these points, so you obtain a curve C dashed, and this has an Euler characteristic, which is 2 minus twice the genus of C minus the number of points that you've removed. And this is, it's called hyperbolic. The C dash is called hyperbolic if the Euler characteristic is negative. And there's a theorem that's called the theorem of Faulting-Ziegel that says that the set of integral points, or if you like, the OS integral points, is finite. And so, of course, if your genus of the underlying complete curve is at least 2, then C dashed is going to be hyperbolic, and you're just in the, this is just Faulting's theorem. But there are other cases. For example, if you start off with an elliptic curve and you remove a point, so for example, the point at infinity, then the curve is hyperbolic, and the finiteness of the integral points is a theorem of Ziegel. And also, you could start off with P1, so the genus is 0, and then you'd have to subtract 3 points. So for example, you could remove 0, 1, and infinity, and this is hyperbolic. And the finiteness of integral points on here is again due to Ziegel, but in a sort of slightly different form. So maybe if you haven't seen this before, it's worth looking at what are the integral points on P1 minus 0, 1, and infinity. Well, if you start off with just P1, okay, then the integral points are the same as the rational points, so that's K together with infinity. But when you subtract infinity, you want to remove all of the elements of K that reduce to infinity modulo any prime. So you end up with the integers of K. And then when you remove 0 and infinity, well, you're taking the elements of OK and saying, I want to remove anything that reduces to 0 as well. So I end up with the units. And then if you remove 1 as well as 0 and infinity, then you're asking for units such that epsilon minus 1 does not reduce to 0. So epsilon does not reduce to 1 modulo any prime. And so epsilon minus 1 has to be a unit as well. So you obtain, so once you've written this down, you realize that there's a one-to-one correspondence between integral points on P1 minus 0, 1, and infinity and solutions to the unit equation. So epsilon plus delta equals 1, where epsilon and delta are units of the field. And it's in this form that Ziegel proved finiteness. Proved finiteness for the set of units, set of solutions to the unit equation. Okay, here's I'm not going to say it's a famous problem, but it's a known problem, the arithmetic puncturing problem of Hassett and Schinkel. And maybe it's not famous because it's not as famous as it should be, because it is a genuinely difficult problem. The setting is as before. Okay, as Alex said, I really need to take V to be a scheme over OK. But the assumption in the arithmetic puncturing problem is that the codimension of W is at least 2. And so that's one assumption. And the other assumption is that you're going to suppose that the rational points on V are potentially dense, which means that there's a finite extension, f over k, such that the f rational points on V are Tarski dense. And then the question is, are these two conditions sufficient to imply that the set of integral points on the punctured variety, V minus W, potentially dense? So what does it mean for the points on a punctured variety to be potentially dense? It means that there's a finite extension, L over K, and a finite set of places T, such that the integral points here on this, they are Tarski dense in V. So these two conditions are necessary. You can, so obviously if you want the integral points to be potentially dense, you need the rational points to be potentially dense. But also, if you think about the example of an elliptic curve minus a point, okay, elliptic curve, the set of rational points is potentially dense. You just go up to an extension where the Borel rank is positive, but but you see, you have if you remove one point, so that's something of codimension 1, then you have finitely many integral points, no matter what extension you take. All right, so here's an example in the paper of Hassett and Chinko, which is that you take an abelian variety A, and you suppose that the endomorphism ring of A has infinitely many units. So for example, you can take an abelian surface with real multiplication by z square root of 5, and there in that ring you have infinitely many units. Then the integral points on the punctured abelian variety are potentially dense. And the reason this works is because elements of the endomorphism ring, applying an element of the endomorphism ring and reducing modulo prime, those two operations commute. So you end up, so the invertible elements end up preserving integrality. So as soon as you've gone to an extension where you have some integral points, you can construct infinitely many integral points by this action. Here's another example. So David Mckinnon has some papers on this topic with several really nice theorems, but I've chosen, so this is a theorem of Mckinnon and Roth. So I've chosen one that fits in about a tenth of a slide as a sample theorem. So it says if you take a surface V with negative Kodaira dimension, if you don't know what that is, I think it means that over the complex numbers, the surface is rational or it's ruled. Then the integral points on V minus W are potentially dense. What's W? Any subvariety of codimension at least 2. So, but this is one of many theorems. They have theorems about Fano threefolds and so on, but they take longer to state. Okay, so this is as much as I knew before COVID. And then something weird happened a year ago, I was writing an expository paper with Ekin Osman on the unit equation, and this paper by Triantifilou, appeared on the archive with this theorem. The paper is only 3 pages long. And I thought this is a really nice paper, so I worked through the proof and put it in our expository paper. But then I started becoming more and more disconcerted by the statement and the proof. So I'll explain why I find it disconcerting later. But here's a statement. It's very simple. So you've got a number field K of degree n, and I only make 2 assumptions. The first assumption is that the degree is not divisible by 3. And the second assumption is that 3, the prime 3, splits completely in K. And the statement is, if you assume these 2 things, then the unit equation has no solutions. Okay, it's a very simple statement. Now let's have a look at the proof. Well, okay, 3 splits completely. So there's n primes above 3, n is the degree of K, and the residue field for any one of these primes is F3, and the residues in F3 are 0, 1, and -1. So if I take my epsilon, well, it's got to be 0, 1, or -1 modulo P. But of course, epsilon's a unit, so it can't be 0. So it's got to be 1 or -1, and the same for delta. So modulo any one of these primes, if I take this equation here and reduce it, I'm going to get 1 is congruent to ±1 mod P. And you say, well, you see, if these signs are opposite signs, then I'm going to have 1 is congruent to 0, and that's impossible modulo any prime. And if they're both 1, then I'm going to get 1 is congruent to 2, and that's impossible modulo any prime. So they must be both -1, because I get 1 is congruent to -2, and that's okay in F3. So I get that epsilon and delta are both congruent to -1 for all of these primes above 3. And that tells me that, you know, epsilon +1 is divisible by 3, and delta +1 is divisible by 3. So epsilon is -1 plus 3 times an integer that I'm going to call phi, and delta is -1 plus 3 times the integer, an integer that I'm going to call psi. And now, okay, scrolling down, so we got to here. Now I'm going to take these 2 things and substitute them in my original equation, and I'm going to get 1 is epsilon plus delta, so that's -2 plus 3 phi plus psi. And you see, if you rearrange, you take the -2 to the other side, you divide by the 3, you get phi plus psi is 1. Okay, we're almost there. We've almost finished the proof. So we've deduced this equation here. But you remember that epsilon is a unit, and we haven't made use of that fact yet. All we've made use of is that epsilon doesn't reduce to 0 modulo any of the primes. So epsilon is a unit. That means it has norm ±1, and that's you know, epsilon is -1 plus 3 phi. So if I take this norm here and I think of the norm as the product of the conjugates, so I'm going to have -1 plus 3 phi 1 times all the way to -1 plus 3 phi n, where phi 1 to phi n are the conjugates of phi. I can expand the brackets, and I'll see -1 to the n is the degree, plus -1 to the n minus 1 times 3 times the sum of the phi's, that's a trace. And then I'll stop here because I only actually care here about things mod 9. And I look at this, and you see I have a sign here and a sign here, and these two signs have to agree modulo 3. And if two signs agree modulo 3, they have to be equal. So whatever this sign is here, it's exactly equal to that. So if I take it to the other side, I get 0. And then I deduce that the trace of phi must be divisible by 3. And exactly the same thing you can do for delta, and you deduce that the trace of psi is 0 mod 3. And then you can say, well, I can take this equation and take traces. And on one side, I have the 1, trace of 1 is n. And on the other side, I have trace of phi plus trace of psi, that's 0 mod 3. So n is 0 mod 3, and that contradicts my assumption, which I haven't used yet, that 3 doesn't divide n. So we get a contradiction. Okay. Any questions so far? Yeah. All right. Good. So here's the statement again. If 3 doesn't divide the degree and 3 fits completely okay, then the unit equation has no solution. So why did I find this disconcerting? Well, for example, people have been working on unit equations for 100 years, and there's this book by Giori and Iverza. It's about 500 pages on the unit equation, and then someone comes along and in a couple, in a few lines, comes up with a new theorem that is completely orthogonal to anything that we've seen before. But also because you see, although I followed the proof line by line, and I hope you did, I don't really know what technique this is. So Triantafylou says that he's using Chaboty, Coleman, Skolem. But you see, I don't agree with that, because if you go through the proof again, you will realize, and so it's not in Triantafylou's paper, but this is a corollary to the proof. Instead of the units, you take this set V, and this is going to be the set epsilon in K star, such that the valuation is 0 at all the primes above 3, and norm of epsilon is plus or minus 1 mod 9. So norm of epsilon is a rational number, but it doesn't have 3 in its support. And we want this rational to reduce to plus or minus 1 mod 9. So if you take this group, then you will get that this equation doesn't have solutions with epsilon and delta in V. And the crazy thing is that this group has finite index in K star. So it's of infinite rank. So we can't be using anything like Chaboty or Skolem, where controlling the rank is very important. Okay, so but I at that time I was also talking to Alan Krauss and Nuno Freitas about unit equations, and we thought maybe we can sort of generalize this or extend it in different ways. So maybe I should point out that if you go back and you try to replace 3 by 5, the argument fails at this point. So for 5, you have more residues. Epsilon, delta don't have to be plus or minus 1. Triantafylou was constructed a counterexample where this doesn't work when you replace 3 by 5. But we thought that maybe things are better if you, instead of working with a split prime, you work with a totally ramified prime for a reason that I'll explain. So I'm going to momentarily assume that K is Galois and N is going to be the degree of K. G is going to be the Galois group. And I'm going to take a rational prime P, a prime ideal that's above P. And I'll just remind you of the definition of inertia. It's at P, it's the elements of the Galois group such that sigma alpha is congruent to alpha mod P for all alpha in the integer. So they act trivially on the residue field. This is the inertia subgroup. And P is totally, I mean, there's different ways of defining what it means for P to be totally ramified in K, but one of them is that inertia is equal to the whole Galois group. So I'm going to assume now that my prime P is totally ramified, and I'm going to suppose that I have a solution to the unit equation. And now I know that the norm of epsilon is plus or minus 1, but the norm, I can write it as a product of the conjugates. And you see, the conjugates, well, sigma of epsilon is, well, I can, instead of running through the elements of G, I can run through the elements of the inertia subgroup, because they're the same thing. I'm in a totally ramified case. And sigma of epsilon is congruent to epsilon by the definition of inertia, mod P. So I get epsilon to the n, where n is the degree. And so this tells me that epsilon to the 2n is congruent to 1 mod P. I've only used epsilon so far, but I can do the same thing for delta. So I get delta to the 2n is congruent to 1 modulo P, but delta is 1 minus epsilon. So I'm going to get epsilon minus 1 to the 2n is also congruent to 1 mod P. So what do I have now? I've got two polynomials, x to the 2n minus 1 and x minus 1 to the 2n minus 1 that have a common root modulo this prime ideal. So the prime ideal must divide this resultant, the resultant of the two polynomials. But of course, because they have coefficients in Z, the resultant is going to be an element in Z. So the resultant is divisible by my rational prime P that is below this Gothic P. Okay, so what's the upshot? Let me maybe go to the next slide. So the upshot is if I have an extension k over q of degree n, and it turns out that Galois is not needed. Okay, it just makes the argument a little bit more transparent. And if the unit equation has solutions, and if the prime P is totally ramified in K, then P divides this resultant here. Now, what you notice is that this resultant doesn't depend on K, it only depends on the degree of K. So if I fix my degree and I say I'm looking at all number fields of degree K, this tells me calculate this resultant. The primes that are allowed to ramify, totally ramify in K must, if you have a solution to the unit equation, then the only primes that totally ramify in your field K must divide this resultant. Now, of course, this thing is useless if the resultant is 0. So you ask, when is the resultant 0? So I've written an easy exercise. I'm not sure actually if this is, it depends if you think as an algebraist or as a geometer. So if you think as a geometer, you're going to say, well, the roots of x to the 2n minus 1, they lie on the unit circle. the roots of this polynomial here, x minus 1 to the 2n minus 1, they lie on the unit circle shifted by 1 to the right. Okay, so where do these two circles intersect? They intersect at the primitive 6 roots of unity. And so if the resultant is 0, then well, you know what the common roots are. And it means that 2n must be a multiple of 6. And so n must be a multiple of 3. So that's how to do this. So now what I'm going to do is, it's sort of cheating, but it's a nice way to obtain a theorem. I'm going to take my degree to be a prime L that isn't 3, just because of this problem here with 3. So the statement says there are only finitely many degree L cyclic number fields K such that the unit equation has solutions in K. Okay, so why assume? I mean, so let's see why assume cyclic. Why it makes things easier. So if I take K to be cyclic of degree L, P a rational prime, and I'm going to take EP to be. I'm just now momentarily doubting whether this is called the ramification index or the ramification degree. But anyway, this EP divides the degree L, and so it must be 1 or L. And if it's 1, then P is unramified. If it's L, then it's totally ramified. So cyclic number fields of prime degree are nice because everything is either unramified or totally ramified. And if you assume that the unit equation has solutions, then the ramified primes, which are the same as the totally ramified primes, they divide this number, and this number is non-zero. So what we have is we've got a bound on the degree. We know the degree, it's L, but we have a finite set of primes, and we're saying primes outside this finite set are not allowed to ramify in the field. So the theorem of Hermite and Minkowski leaves you with finitely many number fields, or you could use, Kronecker-Weber, because you are in a an abelian field. Okay. So let's see an example. So here's a statement, but an example. If I take L to be 5, okay, so it's a and I just calculate this resultant. I find that it's this number here. So I'm saying I only want degree 5. The only cyclic fields I care about of degree 5 are the ones whose conductor or discriminant is divisible by 3 times 11 times by 3 or 11 or 31. And you can sort of eliminate 3 very quickly. And you end up with just 5 number fields. And we use the unit equation solver in Magma, so that uses an algorithm of De Vega and Smart to solve the unit equation for these 5 number fields. And the only one that had solutions is actually Q zeta 11. So we know for cyclic fields of degree 5, the only one that has solutions to the unit equation is Q zeta 11 plus. And you find for this field, there's 570 solutions. But so this is highly unusual. I mean, normally with Diophantine equations, if you can solve it for one number field, then you count yourself very lucky. So one of the reasons I found Triantafyllu's paper surprising is here's an infinite family of number fields where he could solve the unit equation or show that there's no solution. And this result here is surprising because here we do have
Excuse me,
solutions.
Samir. David McKinnon has a question. He's asking if this is classical for L equals 2.
Yeah, I'm going to come to that in a second. Thank you. Okay. Right. What was I saying? Yeah. So here you have solutions. So it's unusual to be able to solve an equation that has solutions for infinitely many number fields. So what happens? Okay, for L equals 2, it's an easy exercise to show that you only, because I mean the thing that makes higher degree extensions harder is because you don't have a model for the ring of integers. But for quadratic fields, you can solve the unit equation. It was done by Nagel in around 1920, and you'll find that the only solutions are, so 1 plus zeta squared equals 0. Or zeta is the cube root of unity, and you also have 1 plus root 5 over 2 plus 1 minus root 5 over 2 equals 1. So that's the only solutions, either q root 5 or q square root minus 3. And Nagel also solved the unit equation in cubic fields, and he found that there's precisely 2 infinite families. One of them has Galois group S3, and one has cyclic, cyclic. So it fits. So that's, I mean, we assumed L doesn't equal 3 to make the resultant non-zero, but it's a good thing that resultant is 0 when L equals 3, because otherwise this would contradict Nagel's family. Okay. Any questions so far? Right. So maybe, yeah. So
Sorry, can I quickly ask?
Hi. Yeah.
Yeah, with Nagel, are they the only families? Are they all of the solutions?
Yes, exactly. So we do know all of the solutions over cubic fields. They're completely parameterized.
Okay, perfect. Thank you.
Cheers. Okay. But you can't do this over higher fields. It becomes complicated. So I had my COVID vaccine about 6 weeks ago, and I had a bad fever with it for a few days, and I started hallucinating. And one of the things that I was sort of hallucinating about was the punctured abelian varieties, the sort of problem. And why? I mean, so unit equation, that's P1 punctured at 3 points. And there you have a unit group, and you're taking norms, and that's how Triantafilus proof works. And so what's the analog for taking norms, for a punctured curve or punctured abelian variety? And the answer is it's taking traces in the Mordell-Weil group. So this lemma is the conclusion of that sort of hallucination. And it says that if you have an abelian variety, let's make it over the rationals, and P a prime of good reduction for A, and you suppose that the Mordell-Weil group is trivial. So this is a little bit like the analog of norm of a unit is plus or minus 1. Okay, and then you take a number field K where the prime P totally ramifies, and you assume that the degree of K is co-prime to the number of points on a modulo P, then the set of integral points is empty. On the abelian variety where you puncture at the origin. Okay, and so let's look at the proof. So you're in the totally ramified case. So P is equal to a power of a Gothic P, where n is the degree. And let's take a rational point, a k rational point Q on A, and we're going to take its trace. And the trace belongs to a set of Q rational points, and so it has to equal 0, but also, because I'm in the totally ramified case, the trace is congruent to NQ, modulo P. So this is like when we had a unit in the totally ramified case, and we took the norm, we said that's congruent to epsilon to the n. So here, when you take the trace of a point, you get NQ, modulo your totally ramified prime. And well, because it's totally ramified, another fact that we are going to need is it has the same residue field as this, as the residue field of the rational prime underneath it. And I've assumed this condition that n is co-prime to the size of this group. So here, with this equation, because n is co-prime to the size of this group, it tells me that Q is congruent to 0, modulo my prime ideal. So because it reduces to 0, it's not an integral point on my punctured abelian variety. So any rational point is not an integral point. So the set of integral points is empty. All right. So let's take an example. So this is actually, it doesn't immediately follow from the lemma, but it's in the spirit of the lemma. It follows from the same kind of idea. So if I take E to be the elliptic curve, y squared equals x cubed minus 16, I take K to be Q root minus 3, then you can check that the Mordell-Weil group over K is trivial. And now, let me take any prime P that's 2 mod 3. So it's inert in K, and then let's say it's not 2. And I'm going to let Kn be the nth layer of the anticyclotomic ZP extension. So if you don't know what that is, don't worry, it's not important. But it's, the Galois group of this extension is Z mod Pn Z. And if you take the union of all of them, then you get some infinite extension of K whose Galois group is ZP. And what you can show by just a sort of small modification of this is that for every layer, the set of integral points on the punctured elliptic curve is empty. But so why did I choose? This would be true also for the, if you were working with cyclotomic ZP extensions. But for the cyclotomic ZP extension, the Mordell-Weil rank stabilizes very quickly. For the anticyclotomic extension, it grows very quickly. So it is growing like something like P to the n as n goes to infinity. Now, when I was typing these slides this morning, I realized that I don't know the attribution of this. It's definitely a theorem, but I don't know the attribution. So if someone knows, they could tell me. All right. So here's what you get if you. So you might say, well, if I start off with an abelian variety over the rationals, and the Mordell-Weil group is trivial. You know, can I get, and the rational prime L, and I look at the family of cyclic fields of degree L, do I have integral points for finitely many of these extensions? And the answer is, I don't know how to prove this. And the thing that gets in the way is, if I go back one, it's this condition here. Okay, how often is this condition satisfied? But so I'm going to make an assumption. I'm going to assume that there is at least one prime P congruent to 1 mod L of good reduction for A that doesn't divide the number of FP points. So that means that the degree is co-prime to the number of FP points, which is something that we wanted. And now, if I take X to be some large real number, I take the set of cyclic number fields of degree L, so this is and conductor at most K, and I count the ones where I may have an integral point. Okay, then I get densities here. I get a ratio like this, where gamma is some very explicit positive constant that is sort of, you can write an explicit description for gamma in terms of some elements of a certain Galois group. And actually the Galois group that you need, so I said, so assumption 2 here is equivalent to this sort of Galois theoretic formulation, which is that there's an element in the Galois group of this extension, so Q AL, what I get when I join the L torsion of A over Q zeta L. So there's an element that acts freely on AL. So if you take a prime P that does this, then its Frobenius element will belong here and it will act freely on AL. And as soon as you've established that a conjugacy class in a Galois group is non-empty, there's infinitely many, a positive density of prime by Chebytarevs that hit that conjugacy class. So you obtain infinitely many primes, or a positive density of primes P, that do precisely this. And the trick that we've seen in the lemma tells you that if you're going to have a cyclic field of degree L where there are integral points, then the conductor is not allowed to divide, to be divisible by any of these primes. So basically, it reduces to a problem of counting cyclic fields versus counting cyclic fields with conductors that completely miss a certain subset of primes that has positive density. Okay.
We have a question in the chat about a reference for something. I maybe you want to unmute and ask a question.
Oh, yeah.
No, it's where you could find a reference to the result of rank growing very quickly.
Mm-hmm.
That's all. It's not a question.
Okay. Oh, thanks, Armand. Thanks. Yeah. So I don't see the chat at the moment, but I'll look in a minute. Okay. Thanks. So here, I mean, let's take an example. Right. So I should say that it might look like, I mean, this condition 2 is sort of easy to check if you fix your L, because you're searching for a prime P. But you might say it might be hard to check for all primes L, or for all but finitely many primes L. But because of this equivalence, it turns out that it's enough to check that the model representation is large or surjective. So here's an example. If you take this curve C.
Can I ask a quick question, Samir? The gamma was the density of the primes that you don't allow in the conductor?
Yeah, or maybe that's
Or the
divided by L minus 1 or something like this. Yeah, okay. So, right. So take this curve of genus 2. So what I did is I searched the LMFDB for an example of a curve whose Jacobian has endomorphism ring Z, trivial model V group, and I wanted it to be semi-stable. I'll explain why in a minute. So endomorphism ring Z, it guarantees you by a theorem of Sayre that for all large L, the mod L representation is surjective. And that automatically gives you condition 2. Okay, there's an algorithm of Dieulafer to find the set of bad primes where the model representation might not be surjective, and it turns out to be, and this works better if you're semi-stable. It turns out that from Dieulafer's algorithm, you can deduce that if L isn't 2 or 3 or this prime in the conductor, then the mod L representation is surjective, and so condition 2 is satisfied. For 2, 3, and 8,969, you just find a P, and it works. Okay, so the conclusion is that for any prime L and any set S that you choose, there's no integral points on the punctured abelian surface, the Jacobian's abelian surface, for 100% of cyclic degree L number fields. And also for the punctured, so the curve has a point at infinity, a rational point. If you puncture the curve at infinity, you have the same conclusion for the same set of number fields. Okay, right. So the current situation has turned me into a full-time teacher. So I now give a lot of homework. So so I mean, I really haven't had much time to think about these the stuff I talked about today. But every time I have a few hours, I end up writing a 5-page paper. But so maybe I could suggest something if people are looking for a problem to work on, and if you're inclined towards arithmetic statistics. So here's something that you might want to think about. So fix a degree n is going to be a degree for us, and the prime p, and of course there's finitely many étal algebras of degree n over f over qp, and for any one of these étal algebras, you're going to, so I mean, I've just invented notation. So I'm going to define this group H subscript F that of the units in the integers of the étal algebra that have norm when you go down to QP plus or minus 1. And why do we look at this group? It's because if, one way of getting an étal algebra is to start off with a number field of degree n and tensor with QP, and then the units of the integers of the field will end up here. Yeah. Okay. And I'm not sure whether I should call this bad or good, but this set is the set of the étal degree n algebras over QP, where the equation epsilon plus delta has a solution with epsilon and delta in H. So if you fix your n and p, in principle, you can write down all of the étale algebras, and in principle, I'm sure you could write down this bad set. Okay, now here's the hard part, which is to evaluate the proportion of number fields of degree n, where when you tensor k with QP, you end up in the bad set. That should be doable for degree, let's say 4 or maybe 5. Or if you what people in arithmetic statistics often do is work with families that are close to being where the integers are close to being monogenic, and maybe you could restrict to a family like that. But anyway, this proportion, it will be an upper bound for the proportion of number fields of degree n, such that such that the unit equation has a solution, or p1 minus 3 points has an integral point. Okay, and you could probably do lots of things. So I've in the stuff I've written so far, I've concentrated on things where you get density 1, but because it might be easier. But maybe people could do, and you could try this for abelian surface, but maybe you could look at examples where you get positive density results. Thank you very much for your attention.
Thank you very much. Let's unmute ourselves and thank the speaker.